Today's field trip is perfect for this time of year. It's a beautiful day in the early fall. The trees are just starting to turn. A little bit of color is showing up in the woods. And we're heading out west of Montreal along the Ottawa River to look at some rocks of the Grenville Metamorphic belt. So the Grenville is the deep understory of a mountain belt that was formed by the collision of major continents about 1.4 to 1 billion years ago. So this mountain belt was so big and spanning the globe, if you can imagine the Himalayas stretching across Asia, connecting up to the Alps, the Grenville belt is that long. And it's so old. The mountain building event was so long ago that most of the mountains themselves have been completely eroded flat. And what we're seeing here today, cutting across North America and other continents that were previously next to North America, is like the high temperature understory of that, the innards of that mountain belt, where the temperatures got very high, rocks melted, a lot of plutonic igneous rocks were formed there, and the rocks that weren't completely melted experienced high temperature metamorphism. So we're going to see not only evidence of the high temperature metamorphism, we're also going to see the structural deformation that went along with that, formed some fabrics in these rocks, and when those rocks were slowly being returned to the surface by erosion, there was also some lower temperature, kind of moderate metamorphic grade, just a little subtle overprinting and deformation. So we're going to see evidence of all of that. So here's Montreal here on the river. Here's the Ottawa River upstream toward Ottawa. And our gneiss outcrops are about halfway in between on the Highway 50. Now, normally we'd be going out there in vans or buses and we'd be parking off on the side of the road. So there's quite a bit of road noise in the video, and I want to apologize both for that and for the fact that I'm fighting a bit of a cold here. So as you come across the river from Hawkesbury, you're driving on the St. Lawrence lowlands, the Paleozoic sediment that we've seen on Mount Royal, the limestones, shales, and quartzites. As you approach the geologic contact of the Grenville front, you can see that there's a steep scarp in the terrain, that the Grenville rocks are higher. That is because they're more erosion resistant. So it's not actually because they're an old ancient mountain range. It's actually just because when the glaciers came over, they were less effective at scraping away at the Grenville rocks. But I want to give you a view of what it would be like to visit some of these outcrops on Highway 50. What do we do before Street View? So again, in our climate, we have a very wet climate. It's cold a lot of the year, and we have a lot of greenery, so we don't normally get natural outcrops like this. We're quite grateful to the highway department for cleaning this off for us.
Well, here we are at the first road cut where I normally take students on the Highway 50.
We have a lot of rock types to look at today, and actually if we were in the field, we'd see even more rock types. But you're going to see what high-grade metamorphism does to some common rocks. There's a tiny subtle overprint of moderate temperature metamorphism that occurred when the rocks were rising again to the surface or exhuming. We're going to see the foliations or mineral alignments that formed in the rocks during deformation. And then we're going to review the contacts and see how we can tell which rocks are older and use not only the intrusive contacts, but also the structural fabrics to parse out some cross-cutting relationships.
One of the easiest metamorphic rocks to figure out has got to be a metamorphosed granite. That's because the mineralogy of granite is so simple. Feldspar, maybe a second feldspar, oftentimes it'll be a different color. Quartz, a mica sometimes, or an amphibole, and then a few metallic oxides. That's basically the makeup of a granite, and it's easy to identify a metamorphosed granite because all of those minerals are relatively stable across a huge range of pressure and temperature conditions. So the metamorphosed equivalent tends to have the exact same mineralogy, or very close to it, of the original granite. Here we've got a beautiful case of a pink orthogneiss. Orthogneiss is, ortho means that the protolith is an igneous rock, and gneiss means that it's a massive crystalline metamorphic rock that might have banding, but it doesn't split along the banding. So that's to tell it apart from a schist, which has strong mineral banding, and it likes to cleave along that banding. And in this case, we know it's been metamorphosed because it's been deformed. So you can see beautiful long ribbons of quartz. Those would have been more equidimensional grains or equant grains in the original granite. And even the feldspars themselves have small tails or eyes on them. They would have been large feldspar crystals that have been smushed out to an eye shape now. And that's the evidence, so the deformation there is the evidence of recrystallization. That's how we know it's a gneiss. The long axis of the minerals, all being stretched in the same direction, is what forms a fabric or a foliation in this gneiss. Foliation is a rock fabric that's formed by a parallel elongation of lots of minerals. They're all stretched in the same direction, and they're all long in the same direction, parallel. And this particular orientation, this foliation, carries all the way through all the different rock types in these outcrops. So I know that it formed after this mixture of rocks was assembled. That's a kind of cross-cutting relationship. Instead of being a cross-cutting relation between two different rocks along a rock contact, it's a cross-cutting relation that shows me that structural deformation affected all of these rocks, and therefore the deformation event happened after all of these rocks were formed. That pink granitic orthogneiss is in a gradational contact with a much finer grained gray gneiss. The gray gneiss has streaks of different color in it that correspond to the alignment and segregation of different minerals. So this also contains quartz, feldspar, and some micas. I think this has more micas in it than what we would have found in the granitic orthogneiss. I can also see a lot of oxides in here, a lot of little euhedral grains which are rusting out of the outcrop. That tells me that they were an iron oxide prior to the exposure to the surface and weathering here. The grain size of this is much smaller and more regular than what we saw in the pink orthogneiss. Now, sometimes that can be taken as an indicator that the rock is not an orthogneiss at all, but a paragneiss. That means the metamorphosed equivalent of a volcanic or a sedimentary rock, a rock that formed on Earth's surface. Granites can be quite coarse-grained. It's typical to find feldspars and quartz grains in a granite that are a centimeter or sometimes even more. And in this gray banded gneiss, the grains are almost uniformly about 1 millimeter or half a millimeter to a millimeter in size. That's a common grain size range that you would see in a sandstone. So this gneiss, like many other gneisses, it's pretty ambiguous because it's predominantly quartz and feldspar. That's consistent with an origin as a gray granite. It's also consistent with an origin as maybe a sandstone. And it's not always possible to tell in the field without looking at the chemistry in more detail what the original rock would have been. It's also possible that the bulk chemistry changes during metamorphism. Fluids move through the rock and they deposit some elements and they remove others. So it's possible to find a high-grade metamorphic rock for which even the expert geologist can't tell exactly what the protolith would have been. Now, both the pink orthogneiss and the fine-grained gray gneiss contain the same foliation. So we know that they were deformed after they met each other, but we don't know what their original relationship was to one another. Now, walking along the outcrop, I think I found a little bit of a clue that might help us. It doesn't settle the origin of the gray banded gneiss, but it does show us that the pink granite probably intruded into the gray gneiss. So I'm inferring that from the presence of these little wisps of potassium feldspar, pink feldspar, which look exactly like the same color as the pink feldspar that's in the orthogneiss. It also has a similar grain size to that feldspar. So I would interpret these as little intrusions or dikes of pink granite that intruded into the gray gneiss before the development of this foliation, so before the deformation of both rocks together. And that's during that deformation, they got a bit smeared out as the whole rock was getting smeared out to develop the foliation. So if I'm right about that, we have an intrusive relationship between the pink gneiss and the gray gneiss that predates a structural deformation. Okay, we've come upon a plutonic rock, which is a little bit different than the pink granitic gneiss we saw before. For one thing, the ground mass is very dark in color, kind of a dark pinkish gray color. There are large crystals, pink crystals of feldspar here. I know they're feldspar because I recognize the pinkish color, and also because I can see a very strong cleavage in these crystals. This rock also has a very weak foliation compared to the other orthogneiss. But I actually think this rock is less deformed. We don't see the development of those eye shapes or elongated grains in the feldspar. The large grains here that are just hanging out seem to be at lots of different orientations. There is a weak fabric, but it's definitely not as deformed as the other granite. So based on the presence of these big potassium feldspar grains, which appear to be sort of randomly oriented, I'll describe this as a porphyritic granite. And I'm going to stay with that igneous name granite because the foliation is so very weak that I don't think it rises to the level that would be necessary to describe this as a metamorphic rock, as a gneiss. I don't see mineral banding, and I don't see a really strong orientation of the minerals in the ground mass or in these big crystals. So we're going to call this a porphyritic granite. It might actually be a syenite. So upon close examination of the ground mass here, I can't actually find any quartz. That means we wouldn't call this a granite exactly, even though it's dominated by potassium feldspar. It's a less common type of silica undersaturated magma. I think it's a syenite. Here's an example of our syenite, our porphyritic syenite, with a much stronger foliation than we saw in the middle of the syenite body. We're getting right to the edge here. In fact, over here I can see the contact with a more typical orthogneiss. So I think we're getting right to the edge of the porphyritic syenite. And here we see a much stronger foliation. So that actually supports the idea that the middle of the syenite body is less deformed because it experienced less strain, maybe because it's stronger. Here at the edge, when we're near the boundary of the intrusion, the rock was sheared a bit more during crystallization, and that's what produced the foliation. But you can see those big feldspar grains that make it a porphyritic syenite. They go from being rectangular to being a bit of an eye shape. And so an orthogneiss which contains large grains like this that have been deformed into an eye shape is called an Augengneiss, after the German word for eye. Have these rocks been through the same deformation event? And I would tentatively answer yes, because where the foliation is visible, it's actually parallel and very similar to the foliation we've seen in the fine-grained gray gneiss and in the coarser-grained pink orthogneiss. But the foliation doesn't affect the texture of this rock as strongly as the other two. So it's possible that either the rock is a bit younger and intruded later during the deformation stage, so it only experienced a portion of the deformation. It's also possible that this rock, due to its very coarse grain size, was stronger. So even if it was present through the entire period of deformation, it might have taken up less strain because of that, the strengthening effect of having stronger, larger grains. Okay, here we have a very cool relationship, an intrusive relationship between two rocks, one of which shows some evidence of metamorphism and one doesn't. So this is a finer grained but basically equivalent pink granitic orthogneiss to the one we looked at previously. It's composed of potassium feldspar, quartz, a little smidge of plagioclase feldspar, quite a bit of biotite, and magnetite. All of those minerals remain stable from the time that the pluton crystallizes through kind of high temperature metamorphism. But this granite was intruded by a mafic dike, a basaltic dike. This dike was composed of probably plagioclase feldspar and pyroxene when it first crystallized. Those minerals have been metamorphosed, and it's been left with plagioclase and hornblende, which is an amphibole mineral, as the major components. We call this rock an amphibolite. It's very clearly a metamorphic assemblage. So since the amphibolite is actually intrusive into the granite, we know that it's younger, and therefore the host rock must have experienced the same metamorphism as the amphibolite. But studying only the granite, we wouldn't be able to see clear mineralogic evidence for that metamorphism. It's the basalt, because its minerals go unstable at the pressure and temperature conditions of this particular metamorphism, that give us the evidence that this took place. If there was any doubt left, a dead giveaway would be the presence of these beautiful red, round crystals, which are garnets. Garnet can form in some igneous environments, but most garnets, and it's a pretty common mineral, are metamorphic. This dike is demonstrating a bonus feature, which happens to be a favorite of mine as a along a little fault, and it continues up in this direction. So by using the edge of the dike as what we call an offset marker, we can actually measure the amount of displacement on this fault. So the distance between my fingers here, which is the intersection of the top of the dike with the fault on either side, is about 60 centimeters. That's the apparent offset on this fault. We don't actually know if it could have slid a little bit in this direction as well. That's why we call it an apparent offset, because it's just a two-dimensional cross-section through what could be a three-dimensional offset. The appearance of garnets along the trace of this fault also tells us that the faulting took place at or before the rock experienced garnet stability conditions, so pretty high temperatures and pressures. Probably consistent with the high temperatures and pressures that explain most of the metamorphic minerals in this rock and also the development of the foliation throughout. This amphibolite dike displays the same orientation of weak mineral foliation as we can see in the surrounding granite and that we have seen in the other rocks. So although it's not strongly color banded, we can safely interpret that these rocks are part of the original pre- or syn deformation assemblage. That is, that all of the gneisses that we've seen, the amphibolite gneiss, the gray gneiss, the various orthogneisses, all experience the same deformation episode at the same time. A lot of especially the ferromagnesium minerals, the mafic minerals, when they're metamorphosed at moderate temperatures, 400 or 500 degrees, in the presence of water, they can undergo something called retrograde metamorphism. So usually we think of metamorphism as caused by increasing heat and pressure, causing a different mineral assemblage to become stable, and so the rock transforms toward that mineral assemblage. But the same can happen on the reverse path. When a rock is cooling down or experiencing lower pressures because it's actually being uplifted toward the surface of the earth, it can undergo retrograde metamorphism. And sometimes, because there's actually less heat energy available than there used to be for the rock, it actually takes the introduction of water to help trigger kind of elemental diffusion that makes new minerals. So in high temperature metamorphic rocks like this, it's common to see what we call a retrograde overprint, which is little smidges of medium grade metamorphic minerals showing up wherever water was able to get into the rock. If water gets in all the way through the rock and it recrystallizes at the moderate temperatures and pressures, we might lose the evidence of the earlier high temperature history for the rock. But here in the gneisses of the Grenville belt, the retrograde metamorphism is very localized. That is, it only shows up in a couple of spots here and there where the rock was particularly vulnerable to recrystallization while it was being exhumed. The whole belt had to be exhumed. It was all at high temperature, and now it's all sitting out on the Earth's surface. So it all came through those medium-grade metamorphic conditions. But only in places where water got in or the minerals were just right do we actually see that the rock transformed according to those conditions. Garnets in particular, and also hornblende, really don't care for being wet at moderate temperatures. If that occurs, they readily transform into a set of minerals that we know as green schist minerals. The reason why it's called green schist is because several of those minerals are green. Epidote, chlorite, actinolite, those are three green schist minerals that could commonly form in rocks of this composition. They're all green in color, so any one or a combination of them would give the rock a greenish tinge. So we're seeing that in lots of places, faint greenish tinge throughout. Here's a place where those green schist minerals are developed so coarsely that we can actually see their crystal form and identify them. One place where we see a lot of green schist minerals is on these sharp fractures cutting the rock that have grooves or streaks, very straight ones in a particular direction. This is a fault. This is a brittle fault. That means that the rock was strong and not ductile, not hot, and not squishy during a stage of deformation. The green minerals that have grown on the surface give us an estimate that happened at moderate metamorphic conditions, so 400 or 500 degrees. But it shows that the rock was hard at that time. And so that's consistent with these hornblends, which would be brittle under those conditions. So we have several indicators here that there was deformation at green schist facies conditions after the high temperature deformation and high temperature metamorphism. So let's call it an event during exhumation or retrogression. That could have been at any time in the last billion or so years. We don't know exactly when. Much higher in the crust and much cooler than most of the rocks, the conditions that are recorded by most of these rocks. Now here's a gorgeous example of an intrusive contact. Here we have our pink granite, which we know is later than the gray gneiss because we saw evidence that it was cross-cutting the gray gneiss. And here, this raggedy edge divides the granite from this very fine-grained, dark black-green rock, which is actually a basalt, which has probably been just slightly metamorphosed in the green schist facies, that is at moderate temperature and pressures. It hasn't been deformed at all, and these little fingers, little wavy finger shapes along this contact show the thermal effect of this very hot basaltic magma coming in and intruding this otherwise pretty robust pink granite. This basaltic dike doesn't have any foliation whatsoever. In fact, its grain size is so fine that we can infer that it probably solidified into relatively cold rock or near the surface. So this is a much, much later event than the high temperature metamorphism and the deformation which formed the foliation and all the other rocks. This is a much younger rock. This is an example of an intrusive boundary that between two rocks that record very different conditions at very different times.
Okay, so in a nutshell, you can see how at a single outcrop, you can identify a series of rocks, examine their contacts, and interpret the cross-cutting and the relative age relations, and reconstruct a basic geologic history, even without knowing exact temperature, pressure, time, relationships. Those are things that you need to go back to the laboratory to figure out in detail. If we were regional mappers, we would then carry this on to many, many more outcrops across the region to verify that what we found at this one outcrop was really a regional phenomenon, and to add more rock types and more relationships to the history to flesh out the detail. Why would you want to do this? Well, maybe one of these rock types has particular economic value or poses a particular environmental risk. For example, those pyrites can produce acid mine drainage at the surface, and in which case you would want to trace them as carefully as you could through the region, and understanding their relationship to the other units helps you put that sort of thing together.